we are going to look at our next applications of the Octant rule. The compound that we are looking at is a natural product minus menthone. When I say minus menthone, what does it mean? It shows negative rotation at 589 nanometers. Okay. Minus menthone question is whether it has this absolute configuration or it has this absolute configuration. So, we want to determine the configuration. As we said last time, there are three unknowns in this. One is absolute configuration, one is conformation, one is sign of the Cotton effect. We are determining the configuration here. That's going to be first, second, third. Describes anti-clockwise direction. Hydrogen is in front. Therefore, it's your 1R. When I look at this, first, second, third describes anti-clockwise direction. Hydrogen is below. So, this is 1R 4S. Obviously, the other will be 1S 4R. When we look at this, since both our substituents are going to be equatorial, there is no question of what is the conformation. Conformation will be chair, both substituents are going to be equatorial. And this is the 1R 4S. Let us check it out. Describes anti-clockwise direction. Hydrogen is in front. So, that is your 1R. Okay. If this is your absolute configuration, now we are going to draw the octant projection of this. As we said last time, when we draw the octant projection, the carbon number 3 is going to be on the intersection of plane A and plane B. We have to view the model from the side of oxygen. Therefore, carbon number 2 will be on the left hand side, carbon number 4 will be on the right hand side. Carbon number 3 will be at the top, that will be your projection. Methyl group here, that will be your isopropyl. Since isopropyl group lies almost on the plane, its contribution is very small. Therefore, the major contribution is going to be of the metal group. Therefore, the predicted Cotton effect will be positive. Weak positive Cotton effect. And that is what is observed, weak positive Cotton effect. Cotton effect is positive, conformation is fixed. Therefore, absolute configuration is predicted to be 1R4S. Let us show this using the model. That is your blue is the isopropyl, that is your methyl group. Okay. That is going to be your plane A and that is going to be your plane B. I hope everybody sees isopropyl group is almost on the plane B. Plane B passes through oxygen, this carbon and the two adjacent carbons. Plane A passes through these carbons. Okay. So, immediately what do we see? This carbon is on the upper left, the isopropyl group is almost in the plane, makes very small contribution. So, the observed sign is a weak positive Courtney effect. Therefore, the absolute configuration of minus menthone is 1R4S. Is there some confusion here? Here we say minus menthone, then we say weak positive. How can we explain this? So, when I say minus menthone, what it means? At 589 the rotation is negative. Sorry. What is this? Molecular rotation, and it shows weak positive Courtney effect. So, at 589 the rotation is negative, therefore, we call it minus menthone. The sign of the Courtney effect is positive, therefore, there is no contradiction. It only we realize that that minus menthone relates to rotation at 589 nanometers. Okay. So, we have fixed that minus menthone is 1R4S. When I treat minus menthone with a base, it gets converted into a mixture of the starting compound and an isomer. Where will the change take place? Will the change take place at carbon number 1? Will the change take place at carbon number 4? Yes? You are treating it with the base, so what should happen? Acidic hydrogen will be abstract. If I pull out this, there will be no change, but when I pull out this, I will create an anion, and an anion picks up hydrogen from lower phase, it will give you minus menthone back. If it pulls out from the upper phase, you will get a new compound which is plus isomenthone. We have changed the stereochemistry at carbon number 4. So, we have converted 1R4S into 1R4R. Direction is anti-clockwise, hydrogen is above. So, 1R4S has been created into this. This sign of the Courtney effect, we now know absolute configuration. The sign of the Courtney effect is strong positive, we want to find out what is the conformation. What is our expectation? Since the isopropyl group is the larger substituent, what do we feel? The isopropyl group would prefer to be equatorial. Therefore, I should make ring flip. When I ring flip, what should happen? Axial isopropyl group will now become equatorial. And equatorial metal group will now become axial. When I make the ring flip, this carbon has come downwards, as we have shown, that carbon goes up. So that's going to be so your metal is axial, your isopropyl group is now going to be equatorial. All right. Now what do we have to do next? To apply the octant rule on the blackboard, we like to have that ketone at the head of the chair. I once again repeat that this is not a compulsory statement of the octant rule. It is to ensure that the other carbons are going to be in upper octants. Okay. So, we use our rule of thumb. What does the rule of thumb say? Do this, and you do this, what will happen? Whatever groups are below will become above, and whatever groups are on the lower surface will go on the upper surface. So at first glance, this should be the picture. Okay. So let's if this is the picture, how are we going to draw the octant? Carbon number 3 will be at the center. Miss, where should I write carbon number 4? Left hand side or right hand side? Left hand side. We are always looking from here, please. So carbon number 4 is going to be on the left hand side, carbon number 2 is going to be on the right hand side, what was the expected sign of the Cotton effect? Since these are negative and these are positive, and this is lying almost on the plane, the expected for this conformation would be negative cotton, but the observed cotton is a positive cotton. Okay. So let's show this process. All right. So first is, that was your menthone. Then we treat it with a base. All right. So we made it into this methyl group equatorial, isopropyl group axial. Next stage, we ring flip. When I ring flip, I take this upwards. I hope everybody sees the boat. Do this, you get this picture. This is what we have shown here. All right. Ketone going downwards, isopropyl has come on this surface. Please remember that whenever you draw the chair, this surface corresponds to the surface that is towards you. Okay. So that's your isopropyl group, that's your methyl group. Now we do our department's rule of thumb, go from this to that picture. When I do this, what happens? Isopropyl group has gone on the back surface, methyl group has come on the front surface. Now when I apply the octant, that's your octant projection, your methyl group is on the upper right, and therefore it's expected to contribute negative. The observed picture is strong positive. Therefore, our assumption that isopropyl group will prefer to be equatorial doesn't seem to be correct. All right. So let's go back to the other picture. All right. So if I go to this picture now, isopropyl group axial, that's the picture. Now if I draw the octant projection, your ketone is once again going to be at the intersection. Carbon number 2 is going to be on the left hand side. Carbon number 4 is going to be on the right hand side. That's your carbon number 1. Now what do we see? This will contribute positive, this will also contribute positive. Therefore, we should have strong positive Cotton effect. Okay. All right. Just letting it make sure that's your plane A, that's your plane B. This is going in a lower octant and this is in an upper octant. This is contributing positive, this is contributing positive. Therefore, end result is strong positive Cotton effect. We call this as plus isomenthone. Therefore, if we want to now show the picture, rotation at 589 is positive and it shows strong positive Cotton effect. What are the questions we have to now answer? The question we now have to answer is this. In a cyclohexane, difference between equatorial isopropyl and axial isopropyl is 2.1 kilocalories. But what is the but that is coming in? In this picture, what do we see? That's the isopropyl. It's going to have problem with this, it's going to have problem with this. All right? But when I ring flip, what do I see? now what do I see? This bond and this bond are going to be parallel to one another. This is what is called as the 2-alkyl ketone effect. Substituents in the 2 position of a cyclohexanone eclipse the carbon oxygen bond. In a cyclohexane, they are always staggered, but in the ketone, they become eclipsed. So, in a cyclohexanone, two isopropyl equatorial is more stable than 2 isopropyl axial by only 0.4 kilocalories. That is the point. In a ketone, the substituent at 2 position in equatorial geometry is eclipsing the carbon oxygen bond, and therefore, it does not have the same difference as in a cyclohexane. Okay. Therefore, what is the unfavorable energy here? Unfavorable energy, because isopropyl group is axial, 0.4 kilocalories. Okay. What is the unfavorable energy here? The unfavorable energy here, methyl has now become axial. In a cyclohexane, the difference between axial methyl and equatorial methyl, free energy difference 1.7 kilocalories. But look at something. In a cyclohexane, what would happen? This methyl would have interaction with this hydrogen, it would have interaction with this hydrogen. But in a ketone, it has only large interaction with this, very small interaction here. That is the operation of the 3-alkyl ketone effect. The 3-alkyl ketone effect, metal equatorial, more stable than metal axial by 1.2 kilocalories. So, this has metal axial unfavorable interaction 1.2 kilocalories. Therefore, this conformation is preferred to this by 0.8 kilocalories. So, in fact, from this example, we learnt that in a ketone, there is a difference between equatorial and axial position at 2 position has reduced considerably. Okay? And we also learnt what is the meaning of the 3-alkyl ketone effect. So, that is final part of the story is out of the 2 chair conformations, this chair conformation is preferred over this chair conformation, and this is confirmed by the strong positive Courtney effect. Okay. Another question has been raised here. That question is, one has an alternative conformation possible. What is that alternative conformation? In a cyclohexane, chair boat energy difference is 5.5 kilocalories. In a cyclohexanone, that difference has become only 2.7 kilocalories. Why? Because in a cyclohexane, in a chair, all hydrogens are perfectly staggered. whereas in a ketone we now have eclipsing at this position. Okay. So, there is another conformation that we can talk about. Do this. What has happened now? This has become equatorial like, this has also become equatorial like. What is the unfavorable energy? 2.7. Okay. Now, what have I done? I have made this into a boat. All right. Both substituents are on the same side. Now, we will take again ketone in the boat to the head of the chair. And now, we see something in the boat which is interesting. When I show the plane B now, do you see something? This carbon has gone. Let me show this properly. Okay. All right. Do you see that? Plane B passes through this, this and this. All right. Now, what I see? This carbon is above the plane. This carbon has gone below the plane. Okay. Let us take that to the head of the chair. Okay. Now, let us draw this. That is your isopropyl group. This is positive, this is positive, this is positive. In the normal projection, positive of this carbon is cancelled by positive of this carbon. But now, where is this carbon is positive, this carbon is positive, the methyl is positive. Therefore, it could be some contribution by this. What is the point I am trying to make? Even in this boat conformation, the expected result is strong positive cotton effect. Of course, we realize that boat will not be important at normal temperature because chair boat difference is 2.7 kilocalories. What does this tell us? The boat is a flexible system. The boat has a favorable entropy. Therefore, at higher temperature, you will have more contribution of the boat form. Okay? That is the picture, the story for this. All right. So, we now look at this. All right. We said last time that the axial haloketone rule was before the Octant rule. The axial haloketone rule, 1957. The Octant rule, 1961. Okay. So, what was this axial haloketone rule? The axial haloketone rule says that when you halogenate the ketone, normally the ketone usually enters in the axial geometry. Why does it enter in the axial geometry usually? The carbon hydrogen bond and the pi orbitals of the carbon oxygen bond are parallel to each other. So, when I make the enol or I make the anion, the axial hydrogen is the one that is involved, all right. And therefore, halogenation normally is axial. Okay. What these people observed is, if halogenation is equatorial, there is no significant change in sign or magnitude of Courtney effect. But if halogen is axial, there is a large change either in magnitude or also possible a change in sign of the Courtney effect. Large change either in magnitude or even in sign. That's what they noticed from many examples. And then they postulated this axial haloketone rule. Okay. The axial haloketone rule, unlike the Octant rule, one of its specific condition was ketone should be at the head of the chair. In the case of Octant, we are putting the ketone at the head of the chair to make our job easy to know whether carbon number 3 will be in upper one or lower one. That's why we were doing that. But in case of axial haloketone rule, that was a specific requirement. Ketone should be at the head of the chair. Okay. If the halogen where is this? The halogen is on the left hand side, it will make Courtney effect negative. If it is on the right hand side, it will be positive. That was their statement of the axial haloketone. All right. Why did we All right. Why did I take the Octant rule first? So I can explain this axial haloketone rule from this example. All right. So that's your picture. If it's on the right, what will happen? What will we see? Ketone is on the right, halogen is going in the lower one. Therefore, contribution is going to be positive. If it's on the left, now what will happen? Halogen will go on the lower left and its contribution will be negative. All right. So, what are the ways chemists could find out whether halogen is axial or equatorial before the axial haloketone? Okay. One is UV says that when halogen is axial, in a ketone, in alpha position to the ketone, there is bathochromic shift. Why is this? The orbitals of the carbon bromine bond are parallel to the pi orbitals of the carbon oxygen bond. Whereas if the halogen is equatorial, there is no change in the UV. When I say we compare parent ketone with product. Okay. So that was the UV method to find out whether halogen is axial or equatorial. IR picture is quite the opposite. When the halogen is equatorial, what happens? The IR frequency increases. Why does it increase? When I polarize this, there is repulsion between this. Therefore, very small contribution by this structure, more contribution by double bonded structure. More double bonded structure means larger force constant, means higher frequency. What is this factor called? This is the dipolar field effect. This only happens when the halogen is equatorial. When the halogen is equatorial, what do I see? This negative charge will prevent carbon oxygen bond from having appreciable single bond character. Therefore, more double bond character, therefore higher frequency. So, halogen is equatorial, IR frequency increases. Halogen is axial, no effect on IR frequency. Okay. All right. So, now we come to the application of the axial haloketone. When I do a halogenation, what are the position, whether the halogen has gone this side or this side? Position, absolute configuration, conformation, sign of cotton. Now there are 4 unknowns, and if I know 3 of them, I can predict the fourth. Let us again state the important features. This whole story applies only when halogen is axial. If halogen is equatorial, there is no use to this story. Okay. Then we can have whether the halogen has gone left of the ketone, right of the ketone. What is the absolute configuration? What is the conformation? What is the sign of the bond? So, if I know 3, I can predict the 4th. So, let us take our first example. We want to determine the position of halogen. All. In a normal steroid, that would have been the ring. What we have done? We have broken the ring at this place. We call this as a cholecystane 2,3-dioic acid. We have broken the bond between carbon number 2 and carbon number 3 and made it into a dicarboxylic acid. If I have to give the full name, 5-alpha 6-keto cholecystane 2,3-dioic acid. As I mentioned last time, the only stereochemistry that changes in a steroid is this. That is why we specify this. Oxygen is at 6th position, so 6 cholecystane 6-zone 2,3-dioic acid. Okay. Why choosing this compound? Why choose this compound? Number 1, as it is a steroid, absolute configuration is known. What is known? 5-membered ring is always on this side, ring A is always on this side. So, absolute configuration is known. Number 2, conformation is known because it is a trans anti-trans Sankhya, conformation is known. Okay. So, we brominate this. When I brominate this, bromine can go at 5 position or bromine can go at 7 position. Both positions are adjacent to the ketone. We know the absolute configuration because it's steroid. We know the conformation because again it's a trans-anti-trans structure. We know the sign of the cotton effect. Therefore, we will find out whether bromine has gone at 5 position or 7 position. But before that, we must know whether bromine has gone axial or not. So, UV shows bathochromic shift. IR shows no change. Therefore, halogen is axial. Okay. All right. Original cotton effect, ketone cotton effect, negative cotton. After halogenation, strong negative cotton. So, large change in magnitude. That also tells us that halogen has gone axial. Okay. If it has gone at 5 position, that would be the picture. All right. So, what's the next job? Before I make ketone at the head of the chair, I must determine the absolute configuration for this. Okay. Five, 6, 10, 4. So, what's the priority order? Yes, what's the priority order? Bromine is first, then carbon is joined to oxygen, whereas carbon is joined to carbon. So, first, second, third. Why is this third? It's joined to 3 different carbons. So, that's the picture. Describes anti-clockwise direction. How is the group last in priority? Group last in priority is above. Therefore, that's your R absolute configuration. So, now comes the problem. When I take this ketone here, where should I write the bromine? Should I write it on upper surface or should I write it on lower surface? One answer is write it somewhere, all right, and check it out. Okay, so we write it. first, second, third. What's the direction? Direction is clockwise. Last substituent is above, so this is S. So what we have done is wrong. So don't think too much. If your imagination is good, do it. If your imagination like me, don't worry, write something. All then you must be very clear of how you find out R and S. Okay, so that's not all right. So where is your bromine? Your bromine is on the left hand side, and therefore expected cotton effect is negative. So if your bromine had gone at 5 position, we would be in a position to get the sign of the cotton effect. Okay. All right. One way was fairly simple, okay, when we doubted whether to do this. Going from oxygen to next carbon is going left hand side. So oxygen to next carbon should go on the left hand side. So that would be the correct way. But even if you have any doubt, write the structure, determine its configuration. If it's wrong, simply cut it, write the right one. Don't worry about it. Okay? All right. Okay. All right. That's your B ring, that's your C ring, that's your D ring. What is this? CH2COH, CH2COH, methyl group, ketone. That's your bromine. Hydrogen here, hydrogen here. Okay. All right. So bromine like this. Take the ketone to the head of the chair. Bromine is on left hand side. Negative cotton should be expected. Therefore, bromine has gone to 5 position. If today you ask such a problem, you will say you must be very foolish. If it had gone to 7 position, NMR will clearly tell you that it has gone to 7 position. But this was days prior to NMR, okay? All right. So today nobody would use this, but this is just to show you the application. Okay. Now, the reason why we took Octant rule first is we can now try to draw an Octant projection for this. Okay. Six position, 7 position, 8 position, 9 position, 10 position. Your 5 position is obviously on the left hand side. Okay. Then your 10 position is here, 9 position is here, 6, 5, 10. Okay. 7, 8, 9. Okay. Now what we are trying to show is this. How are you going to draw the other bonds? How is the bond from 8 to 14? Is it equatorial? Is it axial? Hydrogen is axial, 8-14 bond is equatorial. So, equatorial bond is always like this. That is your 14 bond. How is your bond at 9 position? Hydrogen is axial. 11 bond, what did we say? Axial bond at this place goes down, equatorial bond at this place goes up. That is your 11 position. So, that is going to be our octant. Let us show this. What do I see from this? Everything is on the right hand side. On the left hand side, only these 2 carbons and that bromine going downwards. Okay. What would be the parent ketone? No bromine here. These would contribute negative. Therefore, weak negative. When I have bromine here, bromine will also contribute negative. Therefore, it will be strong negative. All right, everybody is okay? All right, we will have a little break.